So without further ado, Bill Ragsdale, the floor is yours.
Very good. And away we go. Looks okay on the screen, see everything? I'll take that to be yes.
You're fine.
I'll take that to be yes. All right. Local variables. Talk for the day. Clever title, localize your variables. So, quick summary of overview. What are local variables? We're going to talk about what they are, where they came from, and then when to use them. And then we'll explore two different methods that are available for local variables. So this probably for about half of you, this is kind of review, but probably for about half of you, it's probably a new topic because local variables are not in too many Forth systems I've been acquainted with. So possibly on one or two or three of the large commercial systems, they'll be there. But on most of the self-generated kind of exploratory systems, embedded systems and so on, they're probably not there. So local variable is a variable that exists within one word only. And it's a way to offload stacked values into local variables so that you can identify, you can access them by name rather than by their position on the stack. And the most common usage is if you have more than 3 values coming on the stack within either input or within a word, locals are valuable. I'll show a demonstration in here later on where I'm doing some matrix work. And I think at the maximum, I had 15 items on the stack and I would access them with pick and roll. So if you've got 15 values on the stack, you can actually offload all 15 into 15 named variables, and they're much easier to keep track of, especially if you're doing something complicated like a sort. So I looked once, one implementation of quicksort, and doing that without local variables is quite challenging because of the complexity and the simultaneous or near simultaneous quite different actions going on. The contemporary locals behave as if they were a value. That is, executing the word name, the local's name, gives you its value. Now, I think when I first heard about locals years and years and years ago, I think they were acted as like a regular variable where you had to do fetch and store. But all the implementations I've seen lately, they operate as a value. Executing its name gives you the value, and if you want to write to it, you have to use 2 or +2. The most important element is that a local variable only exists within the word in which it's defined or declared. It truly is local. So you have global variables, which are the ones declared overall, and then within one word, you can have local. And you can't not use a local to pass a value from one word to another. The stack is used for that. And one of the restrictions is that the locals cannot be declared within a control structure because they generally use, or in my case, they all use the return stack. So the return stack has to be neutral. You can't have any extra items on the return stack when you declare the locals, because once you've declared the locals, anything on the return stack is inaccessible. So begin, while, repeats, do loops, if then else, and so on can exist. And once you've declared a variable, then you can use it within the control structures. Now, the only problem is the declaration has to be with the return stack neutral. The code is reentrant. I'm misusing this term slightly, but what it does mean is that you can use locals in words that that use locals. So they are independent. If you have a lower level word that has locals in it, its locals are independent of the higher level word. Separate but equal. And today we're going to see two different methods on locals that are in Win32 Forth. When Andrew McEwen did Win32 Forth, his philosophy was, I'm going to be using this myself. I don't care if somebody else uses it. I want everything in it I can think of because I don't want to have to stop and add things to it. So he said, I want under my fingertips all the possible resources. And so locals was one. After he implemented this, a value or a method for locals showed up in ANS Forth. So he added that in too. So here's an example of need. This is a matrix, submatrix copying a submatrix from one to another. And I've outlined the deep stack here. We see things that are 9 deep, 4 deep, 6 deep, 3 deep in the stack. At the end of this routine, there are 7 things remaining on the stack. So we do a 4 drop and a 3 drop at the end to clean up the stack. So if those declarations were made, all of those picked things get replaced with a local name. And at the end, there is no need to do the 4 drop and 3 drop because the return stack and variables are automatically cleaned up at the end of every definition. So here's the syntax, the top line in red with all the little curly braces on it. So the left brace colon begins the declaration, and it is its own compiler. It's its own interpretive compiler. It parses the following statements and looks at it word by word, and it can only accept the proper items within that syntax. So it's its own little parser and compiler. The word Ann and Bob are declared local variables. The stick character in the middle is a separator. I'll come back to that in a moment. Then Carl is another variable, local variable. The double dashes says that all the following is a comment, which is optional. And then the colon right curly brace is the end of the syntax. The variable names before the stick character are initialized from the stack. So in this case, Ann and Bob both would receive automatically the top 2 values in the stack. And the variable Carl is not initialized. So you're quite flexible. You can just declare variables and use them, or you can declare and initialize variables and use them. So the action, as I said just before, the left curly brace accesses the locals variable. There is not hidden, but there's a vocabulary called locals. It's only used for the temporary storage of the local names. So this way they don't appear in your main dictionary and they can only be used within the proper context. That left brace colon sets up a pointer to the bottom of the return stack, does a little housekeeping. It then creates a dictionary entry for each of the names, in this case, Alice and Bob, or Ann and Bob. It returns space on the return stack for each of those variables, and it initializes them properly. Then it moves on to anything that's located after the stick element. In that case, it also creates a dictionary for the name and reserves the space on the return stack, but does not initialize them. And then it ignores anything following. After the last character, the colon right brace, that ends the parsing of the input stream. And then a couple of inline parameters are compiled following that as locators. So here's an example of use. In this case, the word demo, there's the input parameter N1 and an output parameter of N2. With the input parameter of N1 on the stack, we enter and we have the number 200. Now there are 2 items on the stack, N1 and 200. The local declaration is made, and so the variable N is loaded with the earliest value on the stack, and Bob is located with loaded with the top of the stack. So the variables are loaded by values from the stack in the order in which they are on the stack. So it's the earliest in goes to the earliest name, the last data in goes to the last name. And then there's Carl, which is non-initialized, and the declaration is complete. So to test this, to play some games with it and try it out, we're going to do a little do loop. As remember now, the N1 value went into N automatically, and the 200 value went into Bob. So we set up a simple little do loop with the 40 do I plus 2 Bob. So we're just incrementing Bob with the loop index number just to make it change a little bit from its initial value of 200. Then we stick 300 into Carl because it had no initial value. And then to verify what's going on, we do a return, print the word and then contents for and with a dot printed out. And the same with Bob, print out the contents of Bob. And since an output parameter is required, we will then access Carl and leave Carl's value on the stack. So executing this with 100 demo and then printing Carl, what we will see is that and prints out a value of 100, which is what was loaded from the stack. Bob prints out a value of 206, which was the 200 on the stack plus the loop increments. And then Carl comes out with a value of 300, which was loaded in the routine. So it's very well behaved, very clear, very calm, very well behaved. This is the internal allocation that's done in Win32 Forth. The one on the left is a normal usage of locals. In this case, on the return stack, the first value on the return stack is what the stack's address was originally for restoration. And then there's a local pointer, which is saved on the return stack. And then all the values, in this case, local 0, 1, 2, and 3 are saved. Then the return stack pointer is at the bottom, just like it normally would be. And at this point, you can then use the return stack to add and subtract things. And those values above are beyond direct use. On the right-hand side, the word it's used in begins with a :M, and these are, the :M means macro, which really is the object-oriented programming. So there's a slightly different syntax or slightly different storage used. Andrew has a major part of the system done in object-oriented programming written in Forth. It's Forth, but everything is structured as you would for object-oriented. And the integrated development environment and all the editing and ever so much of the utilities are all done in object-oriented programming. So here's the audit programming. ANS Forth came about at the time when locals were not widely accepted or widely utilized, and that the implementations were different. So the conclusion of the committee was that they would mention them, they would give an example or two, or some suggestions for use, but they would not standardize or declare a preferred syntax. So the syntax shown here is the one that they use as a model or as an example, but they said too early to determine if we're going to make a standard value. So in this case, the compiling word is locals with a stick bar at the end. So locals bar says begin a declaration. There are 3 locals named. They are named first, second, and third. And then the stick bar at the end is the end of the parsing. So in this case, you have 3 values. They are all loaded from the stack, and there is no option for an uninitialized variable, although you can handle that quite easily, can be done, no problem. So we see in the explanation there, the locals bar begins. We define named values, first, second, and third, and then end the declaration. It's a little more direct, a little simpler. I believe Andrew used the very same components in implementing this as he did on his preferred version. Here's a demonstration of that alternate syntax. In this case, there are 3 values on the stack, N3, N2, and N1. Declaration is made. And so the value of first, second, and third are loaded. Now, very important, they are loaded in the opposite order from the one that Andrew selected. So in this case, it's last in, first out. So on that declaration, the top of stack is N1, and when the since the first word label name or first variable name is first, N1 goes into first. It's consumed from the stack. Then N2 goes in the second, and N3 goes in the third. So in this case, in our little demonstration, we now change the value of third to 444 and print it out. So what we should see is after first, we should see the N1 value. After second, see the N2, N3, and then we'll see the third value twice. So down below in the red, we input 300, 200, 100, do the demo. We come out in a proper order. And at the bottom, we see 300, which is the contents of third. It's rewritten to 444, and it comes out. So again, very clear. Usage is very, very clear and almost intuitive. Very nice. So a summary. The use of locals is quite convenient and easy. Syntax is obvious. They are very flexible because you can make the declaration anywhere in a word that you want. However, and this is not a drawback, the coding is very, very involved. The coding for a normal value is 1 line of high-level Forth and probably 3 lines of object code, 4 lines of object code, assembly level. In the case for locals, it's about 100 lines of code. About half of it is machine language and about half of it is high level. So it is very involved. However, it's a one-time project. Once it's in, it's in. And there is very little speed penalty for locals because you're reaching into the content of the value. It's got a pointer to the return stack. And so you just have that indirect fetch off the return stack. So speed penalty is very limited, extremely small compared to a regular variable. Personally, I had never even thought of using locals. All the programming I've done using Win32 Forth for the last 15 years, 12 years, I've never used locals. I didn't even know the syntax. I didn't know how they were put together. And to me, it was just, a lack of understanding, so a lack of use. Now I've dug into them, and of course, to understand these, I had to read the source code. In Win32 Forth, there is a help system available, but the help system is written very tersely, and it's written from the point of view of an implementer, not a user. So I looked at that 10 times and didn't really catch the full scope of what the help system was telling me. And so often I had to go back and read the source code, and there's comments in the source code, and then finally it becomes clear. So now I'm comfortable with them. I'll be getting to use local variables. And that is it. Do we have any questions?
Well, I'll make a comment. Am I being heard?
Yes.
Yeah, well, I was looking for the little border. Actually, I've implemented, and wait, I'll show later, I guess. I always looked at it in terms of having stack frames, and I implemented a guy's notion. I found that essentially it just puts the pointer of your current stack and stores that previous one and so forth, but it creates locals too. But I've never actually used them. I mean, they don't initialize. It's just that you know where you have a fixed point on the stack is the purpose. But anyway, I can show that later.
Now, I have a limited experience in this area. I know that UCSD Pascal that came out a long time ago, its calling structure was a stack frame of about 100 bytes. So every time you made a call to a lower level routine, the current environment was saved in a stack frame. And that way the code is reentrant. And I guess there was a way to pass parameters. But you could sort of put locals in that same concept of stack frame, because as you go to lower levels, all those numeric values are on the return stack. And so you could have, say, 3 levels of words called, each using locals, and you'd have all these storage areas on the stack, return stack growing with every time. And the beauty is, of course, it's cleaned up every time, and because every routine has its own protected parameter set, you can reuse the code. I did some work on my matrix package where I had a scratch area, but the scratch area was not reentrant, so it could only be used one time. And then I realized I got myself in a lot of trouble, so I then had to, on every level, I had to generate a new temporary sign. But anyway, any other questions on locals?
I guess mine falls into the realm of comment as well. I wanted to flag for folks that use ESP32 Forth that we do have a locals implementation there as well. And we'll echo your comments about the complexity of the implementation. It was quite tedious to get it right, and there's a lot of fiddly details to get get it to interact properly with things like do loops and so on. There's quite a lot of complexity, but once you've got it, the syntax that I use in ESP32 Forth and Micro E Forth mirrors the one in G Forth, which is fairly similar to the one from Win32, except that instead of a curly brace colon, it's a curly brace. So that's in there, and you've inspired me, Bill, that I probably should also talk about some of the challenges of implementing it, because it was awfully subtle, and then I had folks file bugs and notice I had a case I hadn't handled right, and so yeah, it's a tedious thing to implement.
But here's a question I have that I can't figure out from reading the code. At the end of a word, so you've reached, in execution, you've reached semicolon. So the word is executed all the way through. It's used the locals, it hits semicolon. How do it clean up the return stack? What mechanism does that?
So what I ended, so I can't speak, I haven't looked in depth at the Win32 implementation, but for mine, what I ended up needing to do is that I had to redefine semicolon to do a sweep to check to see in this nesting of this entire word, were there any frames that were generated, and then go through and generate all the cleanup code at that point. And there's a similar dance that has to happen, I believe, with exit, if I'm remembering as well. So there's a couple of different spots that it sort of ends up having to patch the core system to the core words to make it sort of behave itself. And then lots of other wrinkles, like the correct interaction with 2 and +2 and all of those, where they also have to understand the difference between a local versus a value and so on. But yeah,
And
a lot of complexity.
code. Oh yeah, colon, semicolon, and semicolon code. I couldn't see how it could be done without doing that, and so I went back and tried to look at those words and see how they had been patched and modified, and I couldn't tease it out. But that's good. That's all I could think of was you got to clean up at the end of a declaration, at the end of a definition.
Yeah, no, I pondered the same question of, can I do it without touching those? Because for ESP32 Forth, I tried to do the locals all sort of standalone in one file, and I wanted them to have sort of be a thing that could be there or not there, and so I ended up having to redefine semicolon, redefine exit at that point going forward. So yeah, tedious. And the other thing that it ended up being about 72 lines of code, but it's very dense code. The thing I'm actually the proudest of with it was getting it to interact reasonably well with C to be able to decompile a word, because the other danger you get with this kind of thing is you get a word that then can't be decompiled cleanly, and that's another sort of dimension of this.
I appreciate all that deeply. once you start to embellish, the complexities can grow exponentially. Another one is Andrew in here put in a smart forget, because the original Forth used a fixed dictionary tree vocabulary tree structure, so that the vocabularies were linked together at the time they were declared, and so the forget can be somewhat more tame. But with Andrew, with only and also, using only and also, you can dynamically change your vocabulary. And so Andrews has a smart forget that knows the order of definition, and it finds each word and forgets it in the order of definition. So you can say forget anywhere, anytime, and it supposedly will prune everything right back to that point, which
wow. Yeah, I'm sure you would smash the dictionary with if you did forget in the middle of a word with locals and oh wow, yeah, that's amazing.
Yeah, you bet. If you're doing forget, you really ought to be in the Forth vocabulary, and everything else should be clean. Anyway, all right. Well, back to Kevin. Thank you very much for your attention.
Oh my good heavens, I have to unmute now. Thank you, Bill. That was great. Oh, up next, Brad Nelson. How many of you in the audience, show of hands perhaps, except for Bob, have heard of FIQ? Okay, that was exciting. That was the killer app for Forth.